right, third lecture. So we finished the last lecture with the theorem that any birational map between Mori fiber spaces decomposes into Sarkisov links and isomorphism between Mori fiber spaces. Right. And one thing that I wanted to do, but I did not get to, was to remark that these sort of compositions, the compositions are usually not unique. And for this, I wanted to make an example, and one that we have seen already. So, for instance, so I'll do it over R to make it more interesting. So, I'm looking at my map at the inversion at the circle. So this is a quadratic map. It is an involution. It turns the circle inside out, the unit circle. And, well, you can show as an exercise that over C, it is conjugate to the standard Cremona involution. And well, to show this, what you actually need is to find out the base points of this map and the curves it contracts. So, and the base points, they are 0, 0, 1, 1 I0, and 1 minus I0. Right, so this is 1 point of degree 2. Okay, the degree is just the amount of people in the orbit. And what it contracts is 3 lines. And, well, one is z equal to 0, which is contracted onto 0, 0, 1. Big colors anyway. Oh well. and then 2, then degenerate conic. Okay, so these two lines, they are exchanged by the Galois action, and this is just x squared plus y squared equal to 1. And then and we have here these 2 points. Well, that 1 point. So now I want to give 2 ways to decompose this map into Sarkisov links. Okay, so first, so the first option is that we start with the blow-up of 001. So and we end on F1. So we have the strict transform of Z equal to 0. That's a curve of self-intersection 1, and then the exceptional divisor has self-intersection -1. We got the 2 yellow curves and the yellow point, the red point. And now the only thing we can do basically is blow up the red point and contract the strict transforms of the fibers. Right, because they were, so what are this? And so with that, the 2 self-intersection exchange, here we have self-intersection -1, and when we contract the yellow lines, we get the self-intersection 1 and -1 here. And now we are again on F1, and we contract the exceptional curve to a point Okay, so what we did was here a link of type 1, and then here this is a link of type 2 over P1, and then here we go from F1 to P2, so this is a link of type 3. Right. Then the second option. Okay, we start again in P2. But this time we start with the blow-up of the point of degree 2 of the red point. Okay, then what we get is an image that we saw yesterday, actually. So the line Z equal to 0, we blow up 2 points on it geometrically, so it gets a self-intersection, and it has self-intersection 1 here. For each point we subtract 1, so this has self-intersection -1, the exceptional curves have self-intersection -1, and then these two have self-intersection 0 each. And these are the only 3 minus 1 curves geometrically on this surface. And all we can do is contract the white minus 1 curve. So the strict transform of Z equal to 0. And at the end of the last course, I explained that here we end up on a real form of P1 cross P1, which is a quadratic surface isomorphic to xy equal to x square, w square plus z square in P3 for R. So basically this is P1 cross P1, and the Galois action exchanges the fibration. And here we have the base point we have not blown up yet, so that's the point we're going to blow up. On P1 cross P1, geometrically, all these lines here have self-intersection 0. And so these two get self-intersection -1. Okay. And we are basically, again, on a surface like this one. So these 3 minus 1 curves, I forgot to put yellow in it. These are my yellow curves. And these are my yellow curves. Okay. Again, they are exchanged by the Galois action. So now the only thing we can do that is not going back is to contract these two together. Again, they are a Galois orbit of curves. If we contract one, we have to contract the other one. And we get back to P2. There was point, rational point. So what we did here is first, let's see what type of links we used. So is it okay? So this first link is the one we saw yesterday, at the end, that leads from P2 to a quadratic surface. And within the 4 types of Sarkisov links, this is a type 2 link. Okay? It's a type 2 link where the base is a point. And here, and on either side, we have a Mori fiber space over a point. So these are 2 Pezzo surfaces. And then this is of the exact same form, a link of type 2. Okay. So decompositions into Sarkisov links are not unique. They depend on choices that we make. The choices that we have to make are not always obvious, but what is good in this, the kind of nice thing on this theorem is that if the map we want to decompose is very complicated, the proof of this theorem is actually algorithmic. Okay, so, sorry, do you have questions on the decomposition of the map? I was a bit quicker than yesterday because we've seen these links before. So in some sense, the vague idea is what they do is that you pick a base point of the birational map of largest multiplicity and you blow it up. And then, okay, you start with some link, and then for the next link, you take the next base point that has, the next point that you blow up is, again, a base point of largest multiplicity. So basically, they do some sort of induction on the multiplicity of the base point. So yes, from the algorithm, you can get a sort of length, but I don't know how good the length is. That is not clear to me that it does, not at all. Yeah. No, also because you might have different choices of points you want to blow up, and like these points have all the same multiplicity, and yeah. But over algebraically closed field, the algorithm gives you something like, if d is the degree of the map, it gives you something like 4d something linear anyway. And I think that's the best you can actually do. So, but I think that bound is, I mean, you don't really need the Sarkisov program for it a priori. But are there any other questions? So, okay, so since the decomposition is not unique, we want to know about the relations. And here we need to be a bit more group theoretic, I guess, than birational geometers, because there are lots of relations. If I have a relation and I conjugate it with some random element, it's still a relation. So what we want to do is we want to say, okay, we look at the group and then the generating relations. But the issue is that the Sarkisov links don't make up a group, right? Because I cannot always compose, I mean, I can always invert Sarkisov links, but then I cannot not always compose them. I cannot compose this link of type 2, like first this one and then this one, because Q is not F1. So if we want to look at, in a group theoretic way, at relations, what we need to look at are group widths. So here we would say, let's say, Mori of maybe X. This is the group weight of birational maps between Mori fiber spaces. Okay. And the group weight, by this I mean there's this great category way to look at it, but it's equivalent to the one that I'm going to give you. This is a set plus some group law, I'd say, plus some composition. Okay. And plus we can invert and there is an identity, a neutral element. But we cannot necessarily compose. So we cannot compose everyone with everyone. So this is sort of the orthogonal part to a semi-group where you can always compose, but you cannot always invert images. So let's say for this we have some birational maps between Mori fiber spaces, that are birational to X. Okay, to be let's say we have a birational map from a Mori fiber space. Let's say X is a Mori fiber space. And we have some birational map to another Mori fiber space, or Mori fibration. And then we have another one to another Mori fiber space Z over C. And we cannot compose these two maps. I mean, I can do this map and then this map, but I cannot do first this map and then this map. So I cannot always compose. Okay. So let's say phi, psi, first phi and then psi. Makes no sense. But still, for these group waves, we can talk about generating sets and generating relations, like for groups. Okay, so the theorem tells us that this is generated by Sarkisov links. Between Mori fiber spaces, birational to X, and then it has some sort of generating relations, maybe. And what we want to know is what are these generating relations? Well, like, what could they be? Is it okay what I mean by the relations, generating relations? Vaguely. Okay. So, okay, for those, I'm going to make some examples of very simple relations, and we're going to try to. Oh, this was maybe it's too close to my mouth. Okay. We're going to try to see some similarities to guess what these relations, like how we could identify them. So the first relation that I want to say is that we blow up 2 points, 2 rational points in P2. So we have, we blow up, okay, I get confused if I don't stick with the color coding I have on my iPad. So you blow up 2 points. And then Okay, like two rational points. Okay. Two rational points in P2, they are always on a line. Okay. And it doesn't matter in which order we blow them up, right? So we can compute one after the other in whatever order. And then here on either side, we get 2F1. It is not the same F1 because this F1 represents the pencil through the yellow point, and this F1 represents the pencil through the red point. So they don't represent the same pencils. So meaning that Z has two pencils, two fibrations, one coming from this and one coming from this F1. Okay, and then what I can do is contract the line passing in Z. This line has become a -1 curve, and I can contract it. Doesn't look much like a relation, but I can go around this way, or I can go around this way, right? So these are the same ways. And so here I have a fibration over P1, and here I have a fibration over P1. All right. So now the second relation is still I blow up 2 points in P2, but one is a rational point, and the other one is a point of degree 2. I'm sticking today with points of degree 2, so you're going to see a lot of this quadratic surface appearing. So the point of degree 2 was what is the pink one, and then the rational one is the yellow one. So we're going to choose them so that they are not all on one line. Okay? So that they are geometrically in general position. Okay, so we blow up the yellow point, we get to F1, and then we can blow up the red point, we get to the Pezzo surface of degree 7. Every time I blow up a point in P2, the square of the canonical loses 1. Okay, so I blow up geometrically 2 points, the square is 7. And again, they are not on top of each other in any way, so I can commute them. I can commute blowing them up. And I get to some del Pezzo surface, oh sorry, this should be yellow. I get to some del Pezzo surface of degree 6. All right. And now here on X7, just like we did over there, the strict transform of the line through the red point will have become a -1 curve, and I can contract them, and I will get to Q. And this is the same Q that we've got here. And then, so when I contract this line, so blowing up the image of the line or the image of the point on Q, that this commutes as well. Okay, so I can just, I'm going to draw it like this. Okay, Q. So I can blow down the strict transforms of the line starting from X7 or starting from X6. It really doesn't matter. And then, so the yellow point is a rational point. So here I'm blowing up a rational point on Q. Q is a form of P1 cross P1. So Q is a Del-Pezzo surface of degree 8. When I blow up a point, a rational point, I get to another Del-Pezzo surface of degree 7. All right. Okay. And then on the Del-Pezzo surface of degree 7, what I'll have is geometrically 3 minus 1 curves. So it will have and then sorry, not these ones. So I'll have this minus 1 curve, and I'll have geometrically two other minus 1 curves, and those are the the conic passing through the 3 points, the degenerate conic. So this is and I just arrived here by blowing up the yellow point, so I don't want to go back, by contracting the yellow line. So I can contract the white curves, the pair of white curves. And when I do that, I'll go back to P2. Now I can, so here, on this Del-Pezzo surface, I may put the Del-Pezzo surface here maybe. I'll have this picture. Okay, these are the geometric minus 1 curves on the Del-Pezzo surface. Here I blow up the red ones, I blow down the yellow one, and then here I blow down this one, this line, and then here I could also blow down, here I blow down these 2 minus 1 curves, this pair of minus 1 curves, sorry, the hollow action does this. It's very small, but yeah. I can blow them down starting from here. If I blow down a conjugate pair of lines, I lose, for this Del-Pezzo surface, I lose 2, so I get to 5, sorry, I'll add 2, 8. So, okay. Contracting this line, or this pair of lines, commute. So I can complete my square diagram here. And here I'm contracting a rational curve, right? So this is contracting one rational curve onto a rational point. I have F1 here. Okay. And now what we want to see, what remains to see is maybe are these the same F1s, meaning do they represent the same pencil on P1? So this one represents the pencil of lines passing through the yellow point. And then so this pencil becomes this pencil on X6. Okay. Now I'm contracting, so when I go to F1, I'm contracting these 2 conjugate lines. And then when I go back to P2, I'm contracting this rational line. So yes, it is the same pencil that I'm getting here. So this is these are more fiber spaces over the same P1. Was it too quick? Is it okay? Right. I have a third relation, but this one is going to be nicer. We're going to blow up 2 points of whatever degree on a Hirzebruch surface. And we just want here the points that so these 2 points, both are Galois orbits of points over k bar. And we just want these geometric components of the orbit to be on distinct fibers. So this I impose. So we got Fn here. And I have some points, and then a point, and then another point. And I can blow up these 2 points in any order. Okay. And then if I blow up the yellow point, I can, after blowing up the yellow point, I can contract the fiber passing, the strict transform of the fiber passing through this point. So this would be F. What do I get? This is not the moment for me to. So n minus 3. Okay, when I do this, nothing happens to the red points. So independently, I can still blow them up. And then the same story works in the vertical direction. When I blow up the red point, I can then contract the strict transform of the fiber passing through this point. And I'll get to Fn minus 4. And while I do this, nothing is being done on the yellow points, so I can still blow them up here. It commutes with contracting the fibers through the red point, and then finally contracting the fibers through these 2 points. This is independent of each other as well. So I get to complete my blow-up diagram. And then here I get to this. Okay. And these are all maps that I do over the same fibration, right? So so now let's see, what do these, so basically this is just, I have 2 elementary transformations on the Hirzebruch surface and they commute. Okay, this is nothing else. Okay, so what do these 3 relations have in common? Maybe here I'll put some. You're not allowed to say anything. So in all 3 examples, we started with blowing up 2 points somewhere, whose blow-ups commute. So what we did is, so we have here picorank 1, picorank 2, and here picorank 3. So here, and so here the same. We blew up as picorank 1, picorank 2, picorank 3. Here, this has picorank 2, picorank 3, picorank 4. But I forgot something. I forgot to take into account that we are talking about maps between Mori fiber spaces. I have to take into account the fibration that we're working with. And here, P2 is a vibration, a Mori fiber space above a point. It's a del Pezzo surface. And the rho of Z happens to coincide with its picker rank relative over a point, because I'm contracting everything. Okay, and the same story here. So P2 is a Mori fiber space over a point. And so here the relative picker rank of X6 over a point is 3. And what changes is here, because all the surfaces appearing here, even the ones that I didn't put down, they're Mori fiber spaces over P1. They're not Mori fiber spaces over a point. Their picker rank, their picker rank is 2. So these are not Mori fiber spaces over a point, but they are over P1. And so the relative picker rank I should start with is 1. So relative picker rank of Fn over P1 is 1. And then the relative picker rank of whatever is here over P1 is 2. And then the relative picker rank of W over P1 is 3. Okay, so now what I can see suggestively is that there is the variety that is sort of in the middle on top of everything has relative picker rank 3 over the base of smallest dimension. So and while I'm at it, actually, there's a bit more that I can see here. So going from P2 to F1 is a link of type 1. I have relative picker rank 1, relative picker rank 2. Okay. And then going from P2 to Q is a link of type 2. And I have relative picker rank 1, relative picker rank 2, relative picker rank 1. Same here. This is a link of type 2 between fibrations. So I have relative picker rank 1, picker rank 2, picker rank 1. So a link corresponds to something where the top variety has relative picker rank 2. Oh. And by definition, that we had a Mori fiber space was something of relative picker rank 1. So what I'm trying to heavily suggest here is that we have, so picker rank 1, Mori fiber spaces, picker rank 2, Sarkisov links, picker rank 3, relations. So, and I'm purposely putting it in a very non-precise way. Okay. Okay, so maybe for this, let me just repeat the link. So I have. So if I have, let me repeat the definition of a rank something vibration. So a rank R vibration. It's going to be the same definition as a Mori fiber space, only the relative picker rank will be R and not 1. So it is a projective morphism. X to B from a smooth projective surface X to a curve or point B such that. Okay. Now yesterday I said connected fibers, and that is what you geometrically will have in mind, should keep in mind, but then officially it is a bit more than that. And I want the anti-canonical divisor to be relatively ample. And I want the relative picker rank, so the dimension of the space, of the vector space of curves contracted by pi up to numerical equivalence, I want it to be R. Let's see if I've forgotten something. Okay. And then, so the remark is that if R is 1, we have Mori fiber spaces or rank 1 fibrations. If the rank is 2, the relative picker rank, we have corresponds to Sarkisov links. Okay, and let me write down, maybe here I was a bit too quick, but let me write down why. So I have 4 types of links. 1 and 3 are mirrors of each other, okay? So I'm not only going to put 1. So I have, okay, so I have links. I will go from X. So this is type 1, for a point. I'll blow up. Y, and this one has a vibration for B. So in type 1, so I have relative picker rank 1, relative picker rank 1, or as you might, relative picker rank 1, relative picker rank 1. So Y has over a point, it has relative picker rank 2. And then type 2, was of this form. I blow up 1 point and I contract 1 curve. So, and this is a Mori fiber space and this is a Mori fiber space. So I have relative picker rank 1, relative picker rank 1. So again, Y has picker rank 2 over B. Okay, now 3 is has the same diagram as 1, just reflected, so the story is the same. So now, let's see with 4, I have, so this was 2, and then 4. I have 2 Mori fiber spaces. I have 1 Mori fiber space over 2 different bases. I have 2 Mori fiber spaces. No, I have 1 Mori fiber space and 2 Mori fibrations over different curves. So B and B prime are curves. So they have relative pico rank 1 over a point. The Mori fibrations have relative pico rank 1. So the relative pico rank 1 of x over a point is 2. So this is to say, if I have Sarkisov links, they give me rank 2 fibrations. And now the other way around is true too. So given a rank 2 fibration, let's say y over b, so the relative pico rank is 2. That means that I'm going to say some words. If they don't talk to you, that's fine. Don't listen. Just believe it. So this means the cone of curves that are contracted onto B has exactly dimension 2. So it has 2 extremal rays. And so I can have 2 contractions. The 2 extremal rays correspond to 2 contractions starting from y over b. And the contractions, they can be birational, so they can be the contraction of a curve, or they can contract a family of curves. Now, if these 2 contractions are birational, what I get is exactly a link of type 2. Because then I will have a surface here, relative pico rank 1, relative pico rank 1, relative pico rank 1, relative pico rank 1. So here I'll have Mori fiber spaces. Okay, so let me maybe call them A and B. So A and B, they are birational contractions. This is much too small, right? Okay, I'll clean. I'll continue on the other thing. It was too ambitious to put everything on one board. Okay, They are the same as, exactly. Oh, yeah, thank you. Yes, I did not. Absolutely, yes. Yeah. Okay, so what Stefan is saying is that, right, so here, okay, we have one map. You go from P2 over F1 to F1, again to P2. And this is exactly what we are doing here. Okay, this is exactly the same way, the same path. Thanks, that's actually really helpful. And then here, the second option, we go from P2 to Q and then back to P2. And that's going around exactly the other way, P2 to Q and to P2. So thank you. So the fact that these are 2 different decompositions of our quadratic map is represented by, I can do one or the other one, it doesn't matter, and I get the relation. And this relation we see in this square. Maybe I'll write it down before deleting it. I'll try blue for the two paths. Okay, so this was option 1. And then the other one was here. Thanks for the input. Okay, I'll leave it for a bit to contemplate, and I'll just, for everyone like me who has a hard time seeing things from far away, I'll just repeat this. So we are given a rank 2 vibration Y over B, and then so the fact that the relative pico rank is 2 implies that there exists at least 2 is so the space, not the cone of effective curves contracted by pi dimension 2, and then there exist exactly 2 extremal rays. So this means extremal rays should, if you don't know what it is, but it should ring the bell. I can contract something. I can contract a curve or a family of curves. Okay, so I have exactly 2 contractions. Let's say A and B to something, but these contract there over B. Now if A and B are birational, then this diagram here is of type 2. It's a type 2 Sarkisov link, regardless of whether B is a curve or not. So if A is birational and B is not, then B is a fibration. Okay? It contracts a family of curves. And in that case, what we have here is a link of type 1. And then the same, if B is birational and A is not, we have a link of type 3. And if neither of them are birational, then they are both fibrations. And then we have got ourselves a link of type 4. Okay. And so these contractions, they are always relatively ample over, they're extremal with respect to the canonical divisor. Okay, so when I say I got a fibration, that means the fibration is relatively ample. The canonical is relatively ample. Okay, this is an intuitive way to say that rank 2 fibrations, they correspond to Sarkisov links, but up to maybe reflection, because if I have a rank 2 fibration, it could be the top of a link of type 1 or 3. I don't know, but yeah, so, okay. Can I erase the example? Mm-hmm. Yes, but it could be that y is P1 cross P1, and then both extremal rays correspond to one of the two vibrations. Yeah. Yeah. Yeah, we are used to contractions being birational, but we sometimes they just make the dimension drop. So actually, what is written here is the so-called two-ray game. Okay, so if we have a relative Picker rank of 2, then we have always two contractions. They can be birational or not. And then we have exactly two ways to make our surface simpler. Okay? Simpler in some sense. So So if you think, so let's say the example is that if you have y, let's say y is a rational Pezzo surface. No, let's say, yeah, okay. And y has Picker rank 2 for a point, say an assumption. Then you know that, yeah, that's also, let's take our field algebraically closed. And then y is a blow up of, is either P1 cross P1 or y is the blow up of P2 in at most 8 points, simply because it's the Pezzo surface. I don't need rational if we have algebraically closed. Okay, but since y has Picker rank 2, we know that, and P1 has Picker rank 1, we know that we Picker rank 2. So we know that actually r is equal to 1. Okay, So we blew up one point. So, and then if we blow up 1 point, our y is f1, and it has another contraction, and the one to p2, the one to p1. Okay, so this is one contraction, and this is the other contraction. Okay. And here we have seen there are two contractions, and they're towards p1, cross p1. And the two-ray game says basically, so this, if I take a Q, my quadratic surface, my form, why am I? My form of P1 cross P1, where the Galois action of C, the Galois action exchanges the two fibrations. If I blow it up in 1 point, that gives me another Pezzo surface. Then the two-ray game tells you, so since okay, this one has picker rank 1, I blow up something, then XD has picker rank 2, and the two-ray game tells me that there is one other contraction. To somewhere. And the contraction could be birational, okay, or it could be a fibration. So this is what the two-ray game gives you. I'm not going to explain it further, because not everyone might be. So the two-ray game is something that enters the minimal model program, and if you're not used to the minimal program, I think it depasses the course I want to give to explain further where it enters and what it is. So just keep in mind, if I have relative picker rank 2, there are two contractions. They might be birational or not. Okay. So this is what I would like you to keep. I have 1.5 hours, right? Or okay, excellent. Okay, so this is for the rank 2. It was a long explanation of rank 2s. Now, let's go back to rank 3 fibrations, which we want to show that these correspond to relations, or to easy elementary relations. And so there is a theorem that is part, or like a, let's say, I'm just going to write cone theorem here. This is again a theorem that enters the minimal model program, and it talks about extremal rays. And this is let's say, a very particular case for these type of surfaces. So it says that, so if T over B is a rank 3 fibration, right? A rank 3 fibration has relative picker rank 3, so the set of curves that I might be able to contract, they are sort of, so the curves that are contracted to B, they are a 3-dimensional cone, and then there are some extremal rays on the cone, those are the ones that I can contract, and then I have absolutely no control over how many they are. Something is of dimension 2, I have lots of control. They're just 2. It's easy. Cone of dimension 2 are nice. But here, specifically for rank 3, there is a rank 3 vibration, then there are only finitely many morphisms. Over B, starting from T. So I have T, and then B, and I have just a finite number of contractions that I can do starting from T. They might be birational or fibrations. Yes, yeah, exactly, yeah. Yeah, that's the... Okay, so then a corollary of this is that if we have a rank 3 vibration, then so every time, so now we have every time we have a contraction, we lose 1 pico rank. Okay, so let's say I have A1, A2, A3, A4, and we have at the relative rank of each AE is 1. So then when we apply any of those, we get to a, right, so they are over B, so they all factor over B. So when we apply any of those, we get to a something that has relative pico rank 2 over B. Okay? And then we know what happens. We have from something that has relative pico rank, we get to a rank 2 vibration, and a rank 2 vibration is the top of a Sarkisov link. Okay, so rank 2 vibrations. So there are only finitely many rank 2 vibrations such that if I have T or B, I, and I have a rank 2 vibration over C, that I have a diagram that goes, so I have a contraction from T to Y, and then from C to B. Okay. So if pi factors only through finitely many rank 2 vibrations. And then And in particular, so rank 2 fibrations, they correspond to Sarkisov links that are not undirected, okay, that are up to reflection in the diagram. So in particular, there are Sarkisov links. Say chi1 up to chi n. Dominated over B. No, this does not make sense. Let's say dominated by B over B. So what this means is that if I have my Sarkisov link, so let's say I have my link of type 1. Then there is a birational, there's a blow up, and I've got T here, a bit small. And if I have a link of type 2, I have my 2 Mori fiber spaces over some curve over C. And then, so this is my P. I have a birational, I have a blow up to T, and here I'm up to B. And then 3, sorry, the 2 is here, the 1 is here. And for 4, I've got 2 Mori fiber spaces. No, I got one Mori fiber space, 2 Mori fibrations. And I got a birational morphism from P to X that goes here. So in these 2 cases, B is a point. Okay. And okay, what's even more important, or it is important, such that, so if I drew the picture quite suggestively. So here I have a bunch of contractions. Some of them are fibrations over a curve, okay? And no, none of them is a fibration. Yeah, okay. Some of them might be fibrations, but then the ones that are birational, they are these over B. Sorry, the ones that are birational lead to rank 2 fibrations over B. And they represent Sarkisov links. And so what I can do is put Sarkisov links here in a circle around T. And so what they do is they make up a relation. I can start here, follow the Sarkisov links, and I come back here. So in other words, if I look at this relation and I blow up all base points that are involved in each Sarkisov link, I get a common surface, and that's T. yeah, okay, I'll let you copy and then, if you're copying. Okay, and so we call these relations elementary relations. Okay, so what this shows is actually that, so we wanted to, so our intuition told us that simple, so easy relations are correspond exactly to picker rank 3. And what this shows is that rank 3 fibrations, they correspond to nice relations between Sarkisov links. Now, what's a priori missing is the other direction, that the easy relations are rank 3 fibrations, but we're just going to put this as a definition. Okay, so let's say I'm going to this by elementary relations. Okay, so the take home of this lecture is that Sarkisov links, Mori fiber spaces, they have relative picker rank 1. Okay, they are rank 1 fibrations. And Sarkisov links correspond to rank 2 fibrations. They have relative picker rank 2. And then rank 3 fibrations, they correspond to elementary relations between Sarkisov links. And what I want to do tomorrow is to show that the elementary relations generate all relations among Sarkisov links. And then I want to give some applications as like nice things we know about the Cremona group, because we knew Sarkisov links and relations. That's all I wanted to say for today. There are no questions. I assume that everything was clear. No, we don't. You can have a lot. Yeah. So in dimension 2, we do know, but just because there is a list of all elementary relations. Yeah. But in general, I don't think there's a way to give a bound just like that without making the list. Yes. Yeah. I think that's yeah. Yeah. So that would be a trivial relation then maybe. We want to be. If you, as an expert on threefolds, know how to make a bound from above on these, I would be very happy to know. Yeah, this is all over perfect fields. It also works over imperfect fields, but I do not want to go into those. So actually, when you get down to the technical detail, The Sarkisov program is very much linked to the minimal model program. And the minimal model program over imperfect fields has been established by Tanaka. And it works the same way. It basically is sort of like a copy-paste version of the one over algebraically closed fields. So most of the technical grid is exactly the same for imperfect fields as over perfect fields. It's just that you need to, at least that was the case for me, I needed to get accustomed to the fact that I cannot just say, oh, things are smooth, so things work. And then also surfaces might be normal over the imperfect field, but not normal over the algebraic closure. So for me, these were details that where my intuition left me and where I had to start being careful about what the minimal model program does.